your memory. Again, some trig equations were involved using trig substitutions to get the trig functions to be consistent. Our goal is, when we're solving these trig equations, we want to make sure we have an equation that's written in the form of one trig function if possible. So in other words, let's try and get our equation written so that it's in terms of all cosines or all sines. That's the easiest way to solve a trig equation. Or we want to use some type of GCF factoring. In other words, if I can't rewrite the equation in terms of one trig function, can I get a 0 on one side and then pull out a GCF and then set each factor equal to 0? So when you're approaching solving trig equations, this is the strategy where our ultimate goal is going for, trying to rewrite it in terms of one trig function, all sines or all cosines, or can I set it up so that GCF factoring will work? Some trig identities that are commonly used to solve these equations are your Pythagorean identities. So some of you remember from Unit 3, draw the hexagon to help you remember those Pythagorean identities. Remember the three common ones. First one is sine squared x plus cosine squared x equals 1, was one of those Pythagorean identities. The other one was 1 plus tangent squared x equals secant squared x, was the second. And then 1, right up here, plus cotangent squared x equals cosecant squared x. And then, of course, you can manipulate those three and actually solve for sine squared or solve for cosine squared. So Pythagorean identity substitutions will come into play to help us solve some of these equations. We also have reciprocal identities. I'm not going to write all 6 out, but remember, for sine, cosine, and tangent, sine of x is equal to 1 over cosecant of x. Cosine x is equal to 1 over secant x. Tangent of x is equal to 1 over cotangent of x. So just recalling what those reciprocal identities are. We also have those quotient identities. Remember, tangent of x is equal to sine x over cosine x. Cotangent of x was equal to cosine x over sine x. We also had the double angle formulas. So we have your sine double angle formula, remember. So for sine, remember, sine of 2 theta is equal to 2 sine theta cosine theta. The double angles, guys, when you know you're probably going to have to do some type of double angle substitution, is if you see a theta with a 2 in front of that equation. If you see an equation where you see a theta multiplied by 2, that's a red flag that you could be using a double angle substitution to help you set up solving these equations. We also have the cosine double angle. So cosine of 2 theta. Now, on your pink sheet, there were 3 variations of the cosine double angle formula. And again, primarily, most of you are using the cosine squared minus sine squared. But you are going to have to know these other 2 in certain situations when you're solving some of these trig equations. So cosine of 2 theta is cosine squared theta minus sine squared theta. That's the one variation of the cosine double angle formula. You also have the 2 cosine squared theta minus 1. You also have the 1 minus 2 sine squared theta. Now, as long as you remember the cosine double angle, as long as you remember the cosine squared minus sine squared, The reason why you have the other variations of the cosine double angle formula is these come from doing Pythagorean identity substitutions into this original cosine squared minus sine squared. For example, if I take cosine squared theta minus, and if I replace sine squared theta with my Pythagorean identity of 1 minus cosine squared theta, and I simplify that, I distribute my minus sign, I end up with cosine squared theta minus 1 plus cosine squared theta. Then notice if I add cosine squared plus cosine squared, that gives me that 2 cosine squared theta minus 1. So the reason why you have the 3 different formulas is because they take this first one, the cosine squared minus sine squared, and then they're doing Pythagorean identity substitution. So as long as you remember cosine squared minus sine squared, you can come up with the other 2 by doing Pythagorean identity substitutions. All right, so now let's take a look at solving some of these equations. Remember, our ultimate goal is to try and write the equation in terms of one trig function. So here we have cosine theta plus sine theta equals 0. So now, in your mind, what one trig function comes to mind when you think of sines and cosines? Well, by your quotient identity, what's tangent equal to? Sine over cosine. So again, to try and get one trig function in here, I have a sine and I have a cosine. If I want to try and rewrite this in terms of tangent, I know I need a sine divided by a cosine. So what I'm going to do is I'm simply going to take everything in this equation and divide it by a cosine. I could have easily done a cotangent and then divided everything by a sine. So what is cosine divided by cosine? Cosine divided by cosine is a 1. Sine over cosine is a tangent, equals 0 divided by cosine is just 0. So remember, your ultimate goal is you want to try and get one trig function in the equation. And again, when we think of sines and cosines, the one trig function that comes to mind is tangent. Now I have a situation like I had last night for homework. It's a linear trig equation, so I'm going to subtract 1 on both sides. So tangent theta is equal to -1. So where's tangent negative? Tangent's negative in quadrants what? 2 and 4. So the angle in quadrant 2 is going to be at 3 pi over 4. The angle down here in quadrant 4 is going to be at 7 pi over 4. So any questions on example 1? Now let's take a look at number 2. Tangent is equal to cotangent. Again, the goal is to try and get just one trig function in this particular equation. Is it possible for me to change cotangent into some form of a tangent? Yes, because what's cotangent equal to? Cotangent's equal to by my reciprocal identity, it's equal to what? 1 over, you don't want to change in a cosine or a sine. Remember what the goal is. The goal is to have one trig function. We don't want more than one. But what's tangent equal to by our cotangent's equal to what? 1 over tangent. Again, you want one trig function. You don't want to change tangent into sine over cosine. Now you've got 3 trig functions in the same equation. You're not meeting your goal. The goal is using the identity so that you get one trig function in there. How am I going to solve for this? What can I multiply everything by to get rid of the fraction? Multiply everything by a what? Tangent. So that's going to give me a tangent squared theta is equal to 1. Or cross multiplying either way. Now, there's 2 ways you could solve this equation. You could factor, but there's another way you can solve this. How do you get rid of the square? What can you do to both sides? You can take the what? Square root. And remember, don't forget when you take the square root, what do you need to remember to put in front of the 1? You need to remember a what? Plus or minus. So where are you looking? You're looking in what quadrants? All of them. We're looking at all of them in all 4 quadrants. So you're looking at all of your pi over 4 angles. So pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So don't forget when you do that square root, don't forget you have to put the plus or minus there. Or you could have subtracted 1 and you could have factored it as well, whichever you feel more comfortable doing. All right, so any questions on examples 1 or 2? So now let's take a look at example 3. You have a sine squared equal to 2 cosine theta plus 2. Notice you have one trig function to the second power. You have another trig function to the first power. So the goal is you want to try and get this equation written so that you have all sines or all cosines in it. There's really no substitution you can do on this first power cosine. But you do have, when anything's raised to the second power, you do have all of these Pythagorean identities. So how can I get rid of sine squared and rewrite it in terms of cosine? What is sine squared equal to? Sine squared is equal to a 1 minus cosine squared theta. So remember, when you see that square, think of a Pythagorean identity substitution. What kind of equation am I now solving? Is this a quadratic or is this a linear? It's quadratic because you have the highest power of a 2. Remember, if you're not comfortable solving this in terms of cosine, you can do a substitution and write it in terms of x to get you through the algebra. So I could write this as a 1 minus x squared equals 2x plus 2. Now, if it's a quadratic equation, what do we want to have on one side of the equation? We want to have a what? 0. So I'm going to move everything over to the right. So 0 is equal to x squared plus 2x, and when I subtract 1, 2 minus 1 is a 1. So any questions on how I got the 0 on the left-hand side? Now I'm going to factor. X squared plus 2x plus 1 factors into x plus 1 times x plus 1. So any questions on how I factored it? Now this is where you can bring back in that cosine that we did that substitution on. So 0 is equal to cosine theta plus 1 times cosine theta plus 1. And now I can set one of my factors equal to 0. So cosine theta plus 1 equals 0. Get the cosine by itself, so I'll subtract 1. So where is cosine? At what angle is cosine equal to negative 1? Pi. So just the one solution at pi. So like I said, you should zero in on doing Pythagorean identity substitutions when you see a trig function to the second power and a completely different trig function raised to the first power. You can't do anything with this first power, so zero in on the one that's squared and see if you can do that Pythagorean identity substitution. All right, so let's take a look at example 4. Cotangent squared minus cosecant theta equals negative 1. Again, I have a trig function to the second power, a different trig function to the first power. So what I want to zero in on is somehow, some way, getting rid of that cotangent squared and see if I can bring in a cosecant. So looking at your Pythagorean identities, notice cosecant squared is equal to 1 plus cotangent squared. So I can take out this cotangent squared and replace it with your cosecant squared theta minus 1. Right? So again, notice I replaced that cotangent squared with a cosecant squared theta minus 1. So now notice you have an equation that has just one trig function, and that's your goal when you're solving these. You want to try and get them so that you have just one trig function. So now it's a quadratic equation, so I want to solve it by factoring. So I want to have a 0 on one side. What happens when I add 1 to both sides? It gets 0. So I'm left with a cosecant squared theta minus cosecant theta equals 0. So I know I want to try and solve by factoring. Do I have a GCF? I can pull out a what? Cosecant. So I need to set cosecant theta equal to 0. Cosecant theta minus 1 equals 0. Well, cosecant's reciprocal of what? Cosecant's reciprocal of your sine. What's the reciprocal of 0? Undefined. Is there any place in the unit circle where sine is undefined? No. So there's no solutions to that factor there. So now I need to figure out where is cosecant of theta equal to 1, or where is sine theta equal to 1. So where is sine equal to 1? Sine is equal to 1 at pi over 2. So example 3 and 4 are examples of when you're going to need to use that Pythagorean identity substitution. All right, so when you see one trig function squared, a different trig function raised to the first power, that's a red flag to possibly try a Pythagorean identity substitution. So any questions on 3 and 4? Let's take a look at number 5. You have a trig function squared, a different trig function to the first power. So what type of substitution should I try? I should try doing a Pythagorean identity substitution. And again, I want to somehow get rid of this tangent squared, and notice tangent squared is equal to secant squared x minus 1. Now the difference is you have this coefficient of 2. So you're just going to leave the 2 alone and open up a set of parentheses. And tangent squared is equal to secant squared theta minus 1. What do you think I'm going to do next after I've substitute? What am I going to do with this 2? I'm going to have to do what? Distribute. So I have 2 secant squared theta minus 2 minus 3 secant theta plus 3 is equal to 0. Do you have any like terms you can combine? The minus 2 and the plus 3. So minus 2 plus 3, so 2 secant squared theta minus 3 secant theta plus 1 is equal to 0. Now what would you do? Try and solve it by doing what? What would you do next? Well, no, it's a quadratic. We already have all secants, so I'm good. I don't want to do any more substitution. I got all secants, but I would solve it by factoring. So see if you can factor that for me. Just like in algebra land, guys, you learn how to use your calculators to solve different types of algebraic equations. Same thing, and you can use your calculators to solve trig equations. There's lots of different methods that you can use for your calculators. One way, those are probably the 2 different ways your Algebra 2 teachers taught you to use. You use the same techniques as you did back in Algebra 2. You could set your equation equal to 0, and then you load your equation under y1, and then you find the zeros using your calculator. So that's one way you can use your calculator. Another way is you enter your left side as y1, right side as y2, and find the point of intersection. I don't care how you use your calculators to solve the equations as long as you know how to do it. So it's whatever you feel comfortable with from algebra. I'm going to go over both ways with you so you can recall it. So let's take a look at this first example. Again, make sure you are in radian mode. So the first method you could do to solve this equation is to get a 0 on one side. So sine x minus cosine x minus x equals 0. So what you would do is load this left-hand side under y1. So when I go to my y equals on my calculator, I'll hit sine x minus cosine x minus x. Now, using this method, you want to find the x-intercepts. Where is the graph crossing the x-axis? So when I hit graph, how many times is this graph crossing the x-axis? How many times is it crossing? Once. So that means I have one solution. So remember on my calculator to find the x-intercepts, you go under second, trace. So to find the x-intercepts on the calculator, you go under second, trace, and you choose option number 2, zeros. Is this coming back to you guys a little bit from Algebra 2 land? Remember, it asks you for left bound, so you want to move that cursor a little bit to the left. Hit enter. Right bound, move your cursor a little bit to the right, and then hit enter again. So you have to hit enter 3 times. And then the x value is your solution, so x equals negative 1.259. So that's one way your Algebra 2 teachers may have taught you how to solve equations using your calculator. The other method would have been you take what's on one side of the equation and you load it under y1. You take what's on the other side and you load it under y2. So I'll hit my x squared under y1, negative 3 sine x under y2. Graph. This method, what you're trying to find is a point of intersection. So when you use this method, you're looking for points of intersection. How many times are these two graphs intersecting each other? They're intersecting what? Twice. So that means you have 2 solutions. So remember, to find your point of intersection, you still go under second trace on your calculator. But then you want to choose option 5, intersect. And this is where you want to take your cursor and move it so that it's almost right on top of that point of intersection you want to find. And then you'd hit enter the 3 times. So negative 1.722. And then you would repeat it to find the second solution. Okay? Yes, Chloe? Okay, well, you'll have to